Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hey, it's a great pleasure to have Professor Xiaoling Wu from McMaster University to visit Microsoft Research and give us a talk. I know Professor Wu for a long time, who has been active in many areas. The earliest paper I saw from Professor Wu is from his SIGGRAPH paper on basically quantizing images into different color index. And lately, Professor Wu claims to fame with his excellent work on lossless image coding on Calic codec, which has been a long time served as a benchmark for lossless image compression. Professor Wu also has been active in various number of international standards on image compression. Today, let's hear his recent work on standard-compliant multi-description image coding by spatial multiplexing and constraint least square restoration. Without further ado, let's hear what Professor Wu has to say.
Thanks, Jim. Yes, it's nice to see familiar faces in this small group. I don't think that I need to waste my time on the subject area. The topic of multiple description coding has been studied for the last, say, 1 decade, mostly for networked multimedia streaming. Here I emphasize on standard compliance. As I will point out, up to now, all the techniques are mostly represent quite a departure from a current practice. What I will propose is something that is very much in touch with the reality of today's codecs and the infrastructure, and we will appreciate, this technique can be quite practical. And here. Give the outline of the talk. First, I'll give a little bit of motivation introduction, and then I go to the technique called spatial multiplexing for multiple description coding, particularly for image coding. This thing can be generalized to video compression as well, video coding. So the shorthand for this mouthful thing is SMMD. Okay. So after I give the architecture for this technique, this paradigm, I'll go into some detail about how to generate site descriptions and how to conduct site decoding, and then of course, I'm sorry, there was a typo, and central decoding. Okay, then I present some experimental results and then conclude. Okay, so multiple description coding has been promoted as a methodology for multimedia streaming over NAS networks, particularly packet switch networks, for which we have to deal with packet losses and network errors. Okay, and that is because in those applications, particularly for real-time multimedia communications, no transmission is possible because of stringent delay requirements or bandwidth economy considerations. Okay, so we resort to best effort basis, right, like UDP, and the multiple description coding can tolerate, very degrees of losses. Okay, so in other words, we can have a quality of service scalable to network conditions. Right? So the reconstruction quality is proportional to the number of packets we receive. Okay, I'm not going to give a comprehensive review of this class of techniques. Instead, I just highlight some of the common methods for multiple distribution encoding for multimedia. The probably oldest, the quite well-studied multiple description encoding techniques based on multiple description quantization. So we have a multiple description scalar quantizer and a multiple description vector quantizer. And so here we create multiple descriptions by quantizing samples or sample vectors into different representations. This is a generalization of the approach of signal quantization from a single description to multiple description. And then, of course, we have correlating transforms to produce correlated multiple descriptions. And then we have another class of techniques that is also studied in great length by various researchers, that is based on uneven error protection or erasure protection of scalable code streams. So in other words, we apply erasure codes like rate-distortion code and pack the scalable code into multiple layers using various degrees of protection. So therefore, we can guarantee the reconstruction quality is proportional to the number of packets received. Okay, and here, of course, we need explicit forward error correction codes plus a scalable source code stream. Okay, and as we can see, none of those techniques is really standard compliant, right? They represent quite a departure from the current practice. Okay, the question is, can we produce multiple descriptions for media, and while we can work with current compression standards? This is the main motivation of this research. Okay, so what I propose is a very simple, straightforward approach based on spatial multiplexing. So this is the input source. This is a two-dimensional, it could be three-dimensional, even one-dimensional audio, right? What you do is simply just multiplex in spatial domain in the signal space into subsets of those sample grids. And here I deliberately split them into regular sample grids because each of them is an image by itself, so they can be compressed by any existing standard. Okay, now the question is, this simple-minded scheme, will it work? How efficient it can be, and how it compare against other MDC techniques as in the previous slide. Yes?
What exactly do we mean by standard compliant?
Standard applying, okay, meaning
that each description can be decoded correctly by the compliant decoder.
Yeah, okay. Let me show you the next slide. Maybe this will answer your question. So this is the input image, right? I'll do some prefiltering, pre-processing first. Then I split that original image into multiple parts, right? Let's say 2 parts, like a checkerboard, right? And each is a smaller image, right? So therefore, I can use any third-party encoder and a decoder. So in this box, it's a standard, or any other existing technique.
Yeah, but without a proprietary multiplexer, you're not going to get the full resolution image back, right? You get the subset of, a collection of subsets.
Okay, so this multiplexer, I don't think that can be.
On the decoder side, on the decoder side, without a re-multiplexer of some sort, you will not get a full resolution image back.
True. Yeah, but this is the channel, right? The reason we have standards is because we want to have this,
They're all different levels of standards. I know, and
but
unless you, even MPEG is not interoperable at some level.
level, depends on like the packaging, and even the file system.
But then you can make the same argument about other approaches, where can you make them working on, a subset of those can be compliant. What are the descriptions?
For example, Apple's, they use AVC, whatever.
264 ABS, ABC,
AAC for the iPods, but nobody else can. It's proprietary as far as anybody else is concerned, because it's not interoperable.
It's because of the RM. If it's the RM,
yeah, for example, right. So I think this is maybe. We should just take it for example when he says it is. No more, less. It's not really. It's not interoperable at some level.
You can draw a point where.
Right. Yeah. Here.
It's like the operations outside of the compliant operations are minimal and maybe.
And also it's modularized, right? It's completely detached from the channel portion of this whole system, right?
Is because there's like hardware implementations which make it probably complex. It's probably hardware implementations for decoders.
Yeah, but I think in general, I take when anybody says standards compliant, it's like you take it with a big grain of salt because it doesn't really necessarily mean that it's interoperable with anything.
But in this architecture, though, this part, right, is totally independent of what you do with the encoder and the decoder and the channel, right? Whatever you get back at the decoder, you can use it as is. Then, of course, it's not optimal performance, but you can do, as I will explain, in the following, how you can merge those multiple disciplines, right? In case you have more, and then achieve the central decoding, and of course the performance can be scaled according to your complexity at the decoder side. Okay, so yeah, of course what I mean here is each of the side description can be coded by existing standard. I don't have to do special type of MDQ, right? Multiple discipline quantization, or I don't have to do correlating transform or do error correction code to generate some other packets. Okay, so the side description again is generated by uniform spatial downsampling, right? And however, before I do this subsampling, we will perform some adaptive directional low-pass prefiltering for the following purposes, right? First, we will use this prefiltering mechanism to build a bridge between the encoder and decoder. So in other words, I expect, at the decoder side, the decoder will collaborate with encoder to perform MDC decoding. And this filtering operation will also build some correlation between the side descriptions. And also, because it's directional prefiltering, we will preserve signal energy better in the presence of edges, which is, by the way, very important for visual quality. Okay. So this is okay. So this is the design principle and the technique. So first, we set up the design goal of this directional prefilter. So we want to preserve a maximum 2D bandwidth without aliasing due to downsampling, right? So if once we downsample, we reduce the cutoff frequency, right? And then unavoidably we'll get aliasing, right? So now the thing is, how can we, get the maximum bandpass region in two-dimensional spectrum domain without aliasing? And so this is what I mean by those diagrams. You can see, okay, and I can have directional filters, and those boxes represented the pass region in this 2D spectral space, right? And then this is the cutoff frequency in each direction. And so this is for the angles horizontal, and this is for this diagonal angle. This is diagonal. This is tangent 2 to 1 or 1/2, right? I mean, we have those 6 cases. Then you have some other symmetry cases. Okay, and it's easy to show. Okay, there are only 8 directional filters that have the maximum pass region. Okay, the maximum region you can pass without aliasing is pi square. There are only 8 directions that can achieve this maximum region. Okay, and this is it's difficult to have a closed form representation for those cases. So I use this table.
I guess I missed.
Yeah.
So you're going to pre-filter before you
downsample. Yeah.
You're going to pre-filter in a direction theta. Or?
Yeah, I will do. This is the pre-filter design based on different angles.
Okay, you're going to be like image adaptive somehow.
Yeah.
Okay.
That's why it's adaptive to
the
pre-filter.
content. Okay.
To the local gradient.
And then you're going to filter again after at the decoding, the reconstruction side.
At the reconstruction side, I will do the inverse
You'll
filtering.
do the inverse filtering.
Yeah. Right.
Do you mean that you're going to subsample and generate 4 images? Does that mean you're going to use 4 different angles? Apply on each angle?
Okay, so here, right? I will. So this is an example. I can produce 4 descriptions. I can also produce 2 descriptions.
Yeah.
For instance, let's say, right, in each of those cases, the sampling rate is reduced by half, right? Right.
Okay.
So the cutoff frequency is reduced by half. So under this condition, let's say I apply this scaling factor by half, reduce the sampling frequency by half. Then the question is, what is the best pre-filter without introducing any alias, right? So.
And you're going to filter along the edge or across the edge?
Along the edge, right? Because okay, what do you mean?
Low frequency, like along the edge, right?
Yeah. So
why do you?
Because you want to preserve the edge content. You in that case you achieve maximum energy compaction, right?
Yeah.
So.
But there's already, it's already low frequency along that direction, right?
So that's why you want to preserve that. Because against the edge direction, in the gradient direction, you are going to introduce alias anyways, right? Because you are sampling.
So that's why I'm not quite understanding. Like you have aliasing on edges like anyway, right?
Not if you pre-filter.
Well,
yeah, so that's why
he's
you
pre-filtering in that direction. He's pre-filtering along the low pass. I mean, it's all like zero frequency. So what is there to be gained by?
Because against the edge direction in the maximum gradient direction there is alias. You don't want that, right? So you want to cut off that. So you pre-filter.
But you're not doing any filtering in that direction, right? Or you are?
I am.
Some examples?
Yeah. So for instance, in this case, right, this is the edge, right?
The edge goes like that.
Right. So you see, I mean, the frequency against the edge, the pass.
This is the filter.
Yeah, the filter response. Yeah. Right. So therefore you allow, you allow a very high bandwidth, right, in the low frequency direction, because you are not going to suffer from aliasing.
That's all right. So that's what I meant. Okay. So you're going to do a low pass filtering, kind of smooth out the edges.
Yeah.
Okay.
Right. And against the edges, I smooth, right? Because I know, this downsampling scheme will introduce error, right? So in other words, I want to preserve as much as possible, right? So I want to design the region without aliasing, right? Then the question is, what is the maximum possible region? That is a pi square, right? Because if you take the periodical tiles, right, you don't want those tiles to overlap, right? So then you can see, this is the best you can do in those angles. Okay. So therefore, there are only 8 angles, 0, the horizontal and the vertical, and the tangent half and the 2, right? You have a plus minus, and also you have the diagonal, 2 diagonals. So for those spatial angles, you can achieve a maximum region of a pi square without overlapping without introducing alias.
Sorry, what does W refer to?
Here, that's the bandwidth. Bandwidth in low frequency, bandwidth in high, right? And this is the theta, that is the parameter for the directions. Okay, so for instance, let's use this diagram again. So for horizontal or vertical direction, right? And this is this is 2 pi in width. So your bandwidth is pi, right? And in this case, this bandwidth is much narrower in the low pass range. So in this case, it's not symmetric. Oh, so you have the WL pi over √5, and this is √5 times pi.
So we're basically saying the area of the filter pass, as long as it's pi squared, then we're guaranteed to have no aliasing.
Right. That is without aliasing, on that condition, the maximum region you can pass is pi square, right? Now the question is, what filters, directional filters, can achieve that area? There are only 8 cases.
The edge aligns with your 8 directions. If
Right.
there are edges in between, then you will have aliasing.
Yeah. Then my possible region has to be smaller than pi square without aliasing, right? So that's why I say, okay, I want to achieve the maximum preservation of the frequency without, in this downsampling scheme, right? I want to preserve the maximum frequency without aliasing. Then there are only 8 angles that allow me to achieve that. So that's why I designed those 8-angle prefilters, right? Then of course, in real signal, I have to quantize those edge angles into those 8 cases, right? In some angle in between, this is not achievable. Yes, that is true. Okay, so there are many possible. Of course, this is the ideal filter, right? In practice, you have to use some real filters, digital filters to achieve that. For instance, we can use a sinc function to achieve those directional prefilters. And here you can apply a window function in order to achieve, to reduce the ringing effect. Okay. Now this is the pre. Here is pre-processing. This is prior to downsampling, we apply adaptive prefiltering, and this is as Phil pointed out, right? This is a signal adaptive, right? Point by point, we try to estimate the direction of the gradient, then apply the filter. Okay, after that, we downsample, and then we decompress, right? At the decoder side, we will have this decompressed subsampled image. I would say decompressed, pre-filtered subsampled image, right? And then our goal is to reconstruct the original from this downsampled compressed image. Okay, and so let's look at a one-side description. If we get only 1/4 of the samples like this, and then this is the reconstruction problem. And to achieve this, we apply a so-called windowed autoregressive model or wall model. So in other words, we assume the image is piecewise stationary. So in a small window, we can apply this autoregressive model. Each pixel can be written as a linear combination of its labels plus some perturbance term. Okay, and then the regression coefficients alpha here will be a two-dimensional process as well, and we assume that is piecewise stationary. And so in other words, this signal alpha changes slowly. Under this assumption, then we can learn this model in a local window, right? We try to estimate the model parameters alpha in overlapped window fashion. Okay. So this is the technique or algorithm. Let me introduce some symbols. Okay, so X here is represents the pixels in original image I, and Y are pixels in the downsampled image I downsampled here. And W is a local window, and then I use this particular symbol I diamond T for the 4 connected labels of a particular pixel Xi. I is the two-dimensional index for the pixel position, and here the plus means the 4 connected labels for a particular pixel Xi, and likewise X cross represent the 8 connected labels of a particular pixel. Okay, and the task is to estimate a block of high-resolution pixels, the original samples X in this local window, using this autoregressive model. So I have 2 models, okay, model A and B. Okay, so maybe I should use a diagram to show this. Okay, so this is the current pixel X, right? It's 4 diagonal neighbors, 8 connected labels, and the symbol is X cross, right, with respect to I. Okay, so this is 0, 1, 2, 3, the offset. And this is another spatial configuration, current sample in relationship to its 4 connected labels, north, south, east, west, right? Like that. Okay, so I will use 2 models in 2 spatial configurations to estimate the center pixel Xi. The reason I use 2 instead of a single order 8 model is because I want to avoid data overfitting, because I have to estimate those parameters A1, A2, those regression coefficients locally, right? If I have a too high order, then I may not have enough samples to do this properly. Okay, so I split that into 2. So I have 2 models to fit the unknown pixel Xi. Okay. T is the labels, right? Okay.
Index of the neighbors.
Yeah, T is index of labels, and so here 0, 1, 2, 3. So it's just right, and then of course I have a diagonal model. I have an axial model, right? I need to optimally blend them. So there will be 2 weights to be determined, Xi cross and Xi plus, right? And I'll explain how those weights can be computed. Okay, so this is the overall objective function on which we try to estimate the original pixels I. X in a local window W. Okay, so you can see this is a yield post problem, right? Because here I actually have the relationship between the unknowns, right? Okay, and then there are a few loose ends we have to tie up. First, how to determine those coefficients A and B, and also those weights. Suppose we have them, right? Then, you know, we still have a yield post problem because this cost function may allow a trivial solution, right? If I put all those X, I estimate a flat signal, then this will be minimized, right? So if I make the two-dimensional waveform in this window flat, right? So therefore I need a constraint term, right? So what do we know? What we know is this decoded image Y. So, okay, so Y is the pixels in the decoded downsampled image, right? So therefore, this X convoluted by this prefilter, right, will agree to the decoded image. That's what I receive, right? Then of course, remember Y is compressed, so therefore I still have a reconstruction error on Y. So eta of R here is the rate of this compression scheme, right?
Basically given
the quantization error. Yeah.
Okay.
So this is this is the compression distortion, right? Okay. So I want to have the best model fit subject to this constraint. This constraint is given by the system, right? So this is the prefilter I used at the encoder side, right? So this is the received compression image. Okay, this is the quantization error estimate. Okay. I want.
But you're only. This is for. Are you only receiving some?
I only receive one side description.
One description.
One description, which is a downsampled compressed version of I, right? And those Y values alone.
Okay.
That's the only thing I can observe. This is received image, but this Y, right? But I know the original image convoluted by that directional filter, downsampled minus that, should be the
Convolution includes the downsampling.
Yeah, prefilter downsampling. Yeah, the cascade of those two operations, and I know, right? This difference should be the quantization noise. Okay, so I try to get the best model fit subject to this constraint. This constraint is due to the pipeline of the filter in downsample and the compression, right? Okay. So now we have to solve those problems, how to estimate A and B, and how to determine those weights. Okay, so this is the way we compute the coefficients or the model parameters for the diagonal model and for the axial model. So again, we use just solve this linear least square problem, try to estimate the model parameters, right? So we take a small window and fit. And here, of course, we can only use as observables. Those are the decompressed pixels, right?
When it's the decompressed samples, you don't have that high sample, right? I mean, you have the YI. Do you have the cross and the plus?
Yes, I mean, if it's even it's downsampled, I still have the square lattice, right? I still have the cross and the diagonal and the axial correlations to rely on. But you got a point. Yes, in this case, the scale has changed, right?
Okay.
It's because it's downsampled. So therefore, in terms of the step size, it's doubled, right, in spatial domain.
Okay.
Yeah. So here, of course, we have to make assumption that the covariance matrix does not change by downsampling, which is a big assumption, right? But for large-scale edges, this may be a reasonable assumption, right?
Okay.
Right? If the edge or structure have a large scales, then so for instance, if it's straight line and the directional correlation does not change, so that's why later you will see, this technique has some merits. So you can reconstruct edges very nicely. That is because those model parameters can be satisfactorily estimated from the signal y, from the downsampled signal y. So this is how we build the model, right?
How do we go from the previous equation, the previous slides, to these, where over there we want to minimize the joint?
So here,
this
right?
projective function, then you go down to the next one is to decouple the two. For a A parameter, you just minimize. These two are not the same, right? So there's a step to go from this.
Okay,
to
so right. So this is the objective function for the entire task, right? And here we have to know the model parameters A and B. The next slide just shows how to estimate A and B.
Estimating A and B this way, does that guarantee you that the overall objective function will be minimized?
Okay, yeah, that's an excellent point. If I say I want to minimize this objective function by treating both x, A and B, all of them as optimization variables, I can do that, right? But then it becomes a non-linear least square problem, which is much harder, right? So what we adopt this approach is a separation approach. We first estimate A and B, and then plug in the estimate A hat and B hat into this objective function, and then try to solve this problem. Then this problem becomes a linear least square problem, which has an efficient solution, right? But then, of course, yes, we have also tried the nonlinear approach. So in other words, this minimization is not only with respect to x, right? We also search through A and B, try to do this, right? But
let's see your next slide.
okay.
So you're training the A's on your receiving
Y.
signal, but those are downsampled, right?
Right.
Right.
So
But the
Jing
A's
asked the
supposed-
same question, yes.
There's a mismatch, but he's not minimizing over A and B in the other one. He's taking approximation, assuming A and B are known, but he minimizes over x. When the minimization is over x.
Right. So, I mean, ideally, yes, this A and B should be estimated from x, right? From Yeah, but, that becomes a nonlinear problem, right? So what we do is, try to do it in 2 steps.
Okay, but it's not even on the same resolution, right?
Right.
So but A is supposed to be a predictor
For
of
the
highest resolution.
for high resolution, yes. But in this formula, A and B are estimated from the low resolution. Yeah. But computationally, you can but then this is chicken and egg situation, right? I don't know x, how can I estimate A and B? Without A and B, how can I know x, right? Because x will be interpolated from y.
Sure. Well, you could do, another approach might be you train on high resolution images and you send the coefficients over to the decoder and you reconstruct maybe with a fixed filter, maybe.
Right, but that I think that is highly signal dependent, right? So it depends on how much side information you want to send, right? Yeah.
This is not for the whole image. These parameters change per pixel, right?
Yeah. So this is point by point estimate.
That would be probably too much.
Yeah, too much side information. And then of course another thing is you use a training set in like VQ design, and then you don't send.
Right.
But okay. Anyway, those are the
The question is, if you have a signal x, then you downsample that by 4, how does that best linear predictor compare compared to the one before you downsample.
Yeah,
I
exactly.
can take that it's probably not too far.
Okay.
If the signal is oversampled.
Like,
Yeah, right.
yeah, like if I get closer to you, maybe the statistics don't change all that much compared to.
It's oversampled.
Yeah, this is the basic assumption we have to make, right? I mean, if the signal structure is large scale, then this is okay, right? As you said, I mean, the covariance matrix don't. I mean, those things don't change. Signal order statistics don't change that much, right? If original sampling rate is high enough.
Yeah. You're missing
Right.
half of frequency. The low frequency interpolation will be okay.
Yeah, and so this is how we determine A and B, and then this becomes a linear least square problem, right? And then of course we have to compute those weights. Those weights can be okay. By the way, I have to say something about this is an important term. This this constraint, right? Because the original estimation problem is yield post. So many solutions can satisfy that. So therefore, constraints play an important role. The constraints here, I already explained, right? This is the cascade of prefiltering plus downsampling. This is the original image we try to estimate. This is the compressed version we receive, right? So this is the system constraint. Okay. Okay. So here we have to know, because the prefilter is adaptive, right? It is changing from point to point. So therefore, we have to know this prefilter kernel. Okay. Because we use a directional filter, we don't need to send that information. The decoder will try to estimate the direction at the same spot and then make a guess about the prefilter that encoder uses. So it turns out this estimate is quite good, right? We don't need to send any side information. Okay, so the weights of those two models are determined by just this classic linear least square weights, right? And those error terms, error plus, error cross, are the estimation errors of those two objective functions that we use to estimate A and B, right? So they represent how good those two models fit in a local neighborhood, right? Then we just use, assuming those errors are independent, and then we have these optimal weights. Okay, so now we can put all those pieces together and then state the original problem as this unconstrained least square problem. So once we have the weights, we have the model parameters, we have the constraint, right? Then we try to solve this Lagrangian form constraint optimization problem can be solved like this. Okay. Okay. Another interesting interpretation of this scheme is you can consider this as adaptive non-causal predictive decoding, right? So because in that objective function, we try to predict each unknown pixel using its labels. This is a non-causal neighborhood, right? And the predictor is trained point by point, so it's adaptive, right? So I believe this is the reason we get a very good performance, as we will see later. Okay, so you can consider those autoregressive models as non-causal predictors, adaptive one. Okay, and so this is the side decoder. Now, if we get more than one descriptions, then we have to perform the so-called central decoding. So take two descriptions as example. And again, the decoder can be, the encoder and the decoder can be any third-party scheme, right? We will consider our MDC decoder independent of the each side description scheme. Okay, what we do is we do deep multiplexing. So in other words, we can simply just do a mosaic, right? And combine those samples into a denser sampling grid. Okay? And then, of course, because now we have much more information to work with, probably we can do much better than simply just do a mosaic, right? So later, now we'll see how the central decoder can rely on all the pieces of information available to it. Yeah.
Question. I mean, you can see this framework is the least square restoration framework.
Yeah.
I wonder if you can consider other possible framework for the solution. For example, projection of convex set. I mean, so for example, some of the model I see in the past is you model the whole image as Markov-Brandon field.
Yes.
Which is a constraint you put on the whole image. Then the description you receive is a constraint,
right?
Which basically is a convex constraint put on the individual descriptions.
Yes.
You just try to solve this combined optimization problem.
Using, say, conditional Markov field, or even, I mean, you do this maximum likelihood estimate using.
Yeah, you try to estimate the lowest energy point for the constraint, and then basically look back into the constraint to see if it coding to the two description you received. If it's out, you just truncate them back into the and then
to the boundary and
then to the boundary, and then you project again. And
yes.
Thing being used in basically deblocking these kind of things. What do you think about that?
Right, we haven't tried that, but I think that's an excellent suggestion. So, for instance, here we use just a classic D-square approach. We assume it's autoregressive process. We estimate the parameters. I mean, so here we take an adaptive prediction approach. But this kind of relationship could be a Markov field, right? So yes, in this framework, you could have a different reconstruction approach using the decoded image as a constraint, and try to, instead of minimize squared error, you for instance you do EM estimate, or you do maximum likelihood, right? So you can just like it becomes a different estimation technique, right? But nevertheless, this approach will accommodate that, right? I mean, the only thing here is, of course, how to use this. I mean, this is the only known thing, right? This is the only information or the fact we have. We know the original source gone through this kind of a degradation, right? It's mapped to Y. That's the only thing we have.
How big is W?
How big is W? It's 5 by 5, 7 by 7.
So I'm a little confused. Are you tiling the image into these regions?
No. It's overlap.
Okay. So if they're overlapped, then you're just determining what, the center pixel?
Yes, indeed.
Okay. So
yeah.
But the minimization doesn't really
minimize on a single point, right?
Yeah.
Right. So minimization is performed on a block. So you right.
So you find the X in that block, and then what? Just
fix this point X, then move on.
Okay.
Right. And then, of course, that's a good point. If you do this, then for every single pixel, you have multiple estimates, right?
Right.
It can be a center, it could be a corner, right? But then you can fuse them. In fact, you can. If you do this overlapping business, eventually you have multiple estimates on everybody. Right. So that's why Jin said that you could model this as a Markov field. Then you can consider this interplay using some kind of maximum likelihood
so what would
estimate.
happen if you just had a single, estimated a single pixel?
Oh, then the performance will drop.
I mean, your objective would be the single
pixel, and then.
But of course, you're still using your neighborhood and all that stuff. But
yeah. Okay. So for instance, if you only want
constraints are still in the neighborhood.
Constraint is still the neighborhood, and then once you have those parameters A and B estimated, and then it becomes simply just a simple interpolation, right?
It's a matter of how big your stride is when you overlap. He's talking about n-1 stride. 1 pixel stride. So over n-1, if n is your neighborhood size, overlap. Just move 1 pixel at a time. Always get that particular thing. And it just, there's a lot of computation for him. But
Yeah,
probably the best.
but then of course we don't have to fix just single point. We could fix a kernel part, right? As the interior, right? So this is just the implementation. I mean, the most expensive part is I only fix a single point in the middle. Because you see, here we make a lot of assumptions. We think this thing is piecewise stationary. I mean, how about this point is right on the border of a transient, right, edge? Then this window may not.
Okay, yeah. So yeah, I see how this is leading back towards Jin's Markov random field kind of discussion. So I mean,
Right.
I guess I was assuming, supposing you know all the other x's around, then you could reformulate this as find the x in the point in the middle that minimizes some prediction error subject to these constraints.
Yes.
But you don't know all those other.
Right. I mean, all those x's are known as well.
Yeah. So you have to do it instead of doing it all jointly somehow, which would be done in say maybe an iterative mode or Markov random field.
Using message passing, that kind of a trick to do it, right?
Yeah. You're just doing it this way.
Right. I mean, in this way, it's almost equivalent, right? You estimate a block instead of a single point, right? And then, but you move on. So you take a context of a large neighborhood. Okay, so yeah, but then of course, if you have a multiple sub-images, and their spatial configurations, then the same problem can be posted, right, and solved. Okay, so those are the details, I suppose. Okay, and then, yeah, I don't think we need to go into the details, but the one thing we can explain why the central decoder will be more powerful. That is because now I have more constraints, right? If I have two descriptions, I have this checkerboard, right? I have the black spots and then the white spots. For all of them, I can establish, for every point, I can establish a constraint. And also, the model parameters will be better estimated. Now I have more samples, right, if I have more descriptions. And also, remember, we don't send the side information about the filter at the encoder. If I have more samples, then the direction estimate will be better. So I can get a better estimate of the kernel. So all in all, I can improve all those, improve the quality of all the input data for that optimization problem. Then I have a better solution for the central decoder. Okay, so I will show some experiments. We compare this scheme against some recent image MDC techniques. One is done by Jie Wang and Jie Liang, and who used to be here, right? Jie Liang, and he's now at Sam's Freezer. In fact, I will visit him tomorrow. I will drive to Vancouver tomorrow, right? So they published a paper in this year's DCC. They use filter banks for multiple discrete encoding. And then there's another paper, a recent paper, on multiple discrete encoding. Okay, and those two are to our best knowledge, are the best performed methods. Okay, so here's an illustration. Okay, let me explain. This is test image Nina. This is a bike. Okay, and those three solid lines represent those three competing methods. Okay, the one with triangle will be ours. With a circle is a technique of reference one, technique of reference 1, and the dot is another MDC technique from reference 2. Okay, and the horizontal axis is the bit rate per site description, number of bits per sample in each site description. Okay,
And the number of bits per sample in each site description, do you convert it back to the whole image?
no. No, so in other words, here the site description is coded by JPEG 2000 and 0.8 bit per bit. Yeah.
At site, basically images resolution, right?
Yeah, at the smaller resolution, at the right. Okay, yeah. So this is a more complex image bike.
And when you said, so it's a dotted line and a solid line.
Okay, the dotted line will be the side, right? This is the center. Oh, there's two descriptions. So you can see there's a gap up to 3 dB at a high rate, or 3.
Potentially, you can have a total of 4 descriptions.
Yes, we haven't implemented that.
Okay.
So we only implemented 2 descriptions,
Okay.
and the 2 descriptions shift by, half pixel,
Okay.
the optimal shifting, right?
Okay.
So it's a checkerboard, right? Yeah, you can see here roughly 3 dB from a side to center. And the interesting thing is, our side and the center are all above the competing methods. Right? Okay, so I didn't tell the whole story. And when the rate gets higher, those curves will cross. So our scheme has excellent performance at a low to medium bit rate. I mean, that can be understood. That is understandable because we have done downsampling, right? And we basically discard the high frequency signal component. Then, if the rate gets much higher, then this downsampling scheme is suboptimal. So here is another example. So the image flower and the fruit. Okay, so here are the visual comparison. So this is method 1, method 2, and our method at the top row side, and the bottom row is the center. So let me just, can we reduce? Here? No. Oh, at the podium. So this is at the bit rate quarter pixel. Here, right. Yeah. No. Okay. To wrap around. Yeah. Oh, there's a delay. Yeah. Is it dim now? Okay. So I think the visual quality improvement is even more significant than the PSR numbers would suggest. So for instance, if you, particularly at the side, right, the difference is quite significant. Not as much as in the center. Okay, so this is a dark image. So this is a competing method of a site description. Here you can see Thank you. Right, so this is the proposed method SMMD at a 0.4 bit per pixel. This is the MDC technique in reference 1 at the same bit rate. This is the side. This is the center, two descriptions.
And how do these compare to to a single description flutter?
Okay, that I'll come to that point. Single description, say JP2000, right, or DCT, right? Yeah, yeah.
One of my other question is that here I see two technologies may improve basically the performance. One is prefiltering. The other is the least square estimation. Right? Can we see results for the gain for each of the portions? For example, let's say we just apply prefiltering.
Or non-adaptive prefiltering, right?
Let's say we do apply adaptive prefiltering. Let's say we just use a very simple post-processing, so we just do bilinear interpretation at the end. And the other is basically, let's say basically don't do much on pre-filtering. I'm trying to see, for example, visually, the SMMD approach is more appealing than the other approach. I want to see whether the gain, which part of the gain is provided by pre-filter, which part of the gain is provided by least square estimation.
So without pre-filtering, right, you lose something from a 0.3 dB to 0.6 dB in that range. I just had a discussion with my student this morning over the phone. Yeah, I'm talking about the ongoing project.
So pre-filtering provide more gains for the low bit?
No. I think the restoration is more important. Let's say you replace this least square restoration by, as you said, bicubic, right? And then the deterioration will be more than 1 dB, right? If you just do simple interpolation.
But this restoration thing is like, they've been using this sort of thing for, they're super resolution. Yeah.
That's why we found this application. We started with super resolution basically. Yeah.
Like Alan Gershaw would put in like some, just say this.
I didn't know Alan Gershaw did this.
Well, it's I think the way you've done it is probably unique, but but this sort of approach where you use you predict using like a conditional expectation. You predict the pixel that's not there given the surrounding thing,
right,
based on a conditional expectation modeled somehow, and you've modeled it in a particular way. So it's adaptive sort of across the whole image is kind of a common technique. And so it seems like what's more unusual maybe to me is the pre-filtering part. I don't know about which contributes most to the gain here, but
I think pre-filtering contributes, as I said, 0.5 dB is not that much. In fact, you can just do non-adaptive pre-filtering. Okay, pre-filtering, yeah. Okay, remember, we are talking about the MDC, right? So there's a trade-off between the side and the center, right? So in this case, our side description has a fairly good quality compared with some other schemes, right? So that is because the two side descriptions have a fairly high correlation, right? So if you get an additional description, you don't get too much new information. So the center distortion does not drop that much, right? Particularly at a high rate. So the pre-filtering actually can regulate how much correlation you can introduce between the two correlations, right? Because they are interlocked, right? So if you get a larger filter kernel, then you correlate the two better. You have a impulse sampling, then the two are more or less independent. So you favor the center, right? So that is another MDC. That's unique to MDC, right? So, prefiltering will also embed some scheme for the collaboration between encoder and decoder, as I said earlier, because those are the constraints we use. For super resolution, though, those things are out of control, right? That is the point space function. What a point space function gives you, that's what you work with. I mean, here you have the freedom to choose, to design. Yeah, but then I agree. I mean, the framework is the same. I mean, the restoration problem has been studied for a long time. Yes, for instance, deconvolution, denoising, super resolution, right? Interpolation, yes. But I haven't seen, that approach is used in compression, right? So, yeah, and later let's go there. So here, you can see SMND has a much better visual quality than others, even though the Pearson number is actually a little bit lower in this case, right? Okay, so this is due to this particular model we use, right? We use the directional prefiltering, and we use this autoregressive model, which has remember, we have to estimate the model parameters from the low resolution image. That estimate is good if you have long edges or large scale structures, right? In that case, then the signal order statistics doesn't change in scale. I mean, if that's the case, we do a good job, right? So, and also, I mean, in this direction, of course, you have a high frequency, but then, because we do prefiltering like that, and our model will learn this directional correlation well, so we reconstruct those edges much better, say, than those techniques. So this is some advantage we want to emphasize. Okay, and this is from the side to the center, so you see the improvement of visual details. Right, so if you get additional packets, so you can consider this as a scalable code as well, right? Low coarse granularity scalable scheme. Okay, so rate distortion performance remark. So now the question is, if you do this downsampling business, where you necessarily suffer in terms of rate distortion performance, right? So here's my argument, just by water filling principle, we know if this inequality holds, right? In other words, whatever I discard, right? This is the discarded energy from my color frequency. If this part is less than the distortion, given the target rate, this is the distortion function of the source. Then I'm okay. I can safely discard, right? So, for band limited signal, this, and particularly the target rate is low enough, I suppose this,
But that basically means this approach is more basically okay at low bit rate.
Yes.
Or theoretically more safe at a low bit rate than a high bit rate.
Yeah, that's the argument. Yes, indeed, all the experimental results show we have very nice performance at low rates.
How about a high rate?
At a high rate, then we start to lose, right? So this is the side description or the single description, right? Phil just asked this question. So we say, in its own right, this scheme is a superior low rate code. And in fact, it has a higher PSNR than JP2000, which is considered as a very good low rate code, right? And we do better than JP2000 using this deliberate downsampling and at the decoder side, you treat it as an inverse problem and solve it using some knowledge. And so, yeah, this is a table to show some experimental results. So this is just a single side description, which is basically a conventional code now, if you don't get additional descriptions, right? And here are the rates, Lina, leaves, flower, and a bike. I mean, those images I've shown you, right? So this is the bike.
Even with the two descriptions, it's better than...
Even with one description, it's
One
better.
description I can understand is better.
Or two descriptions for the total rate, of course, it's worse.
Yeah.
Right?
I mean,
Yeah,
that-
yeah, yeah, yeah.
In that case, let's say, I mean, you work at 0.3 BPP.
Yeah.
If that 0.3 BPP of the subsampled image, that means, I mean, you're asking the JPEG 2000 to work at 0.075 BPP, right?
I think this is this is with respect to the original size.
Okay.
So in other words, for our side, then the bit rate for single description, the bit rate is 0.6.
1.2? No, it's side, and not base. It's a side description, right?
Yeah, I mean, so this rate is already converted to the original size.
Yes, okay.
Right, original size.
But when you say side, you are using only one description, right?
Yeah, one description. Okay, so for the side, I only have 1/4 of the samples.
Yeah,
So therefore, the original is, yes, 1.2. Yeah, 1.2, yeah.
1/4. So now you have 4 descriptions.
No, this is JPEG 2000 with original resolution, right? It spends 0.3 bit per pixel.
Right.
This side is only 1/4 of the original size.
1/4 of the original.
Size in terms of number of samples. You know, I drop every other row and column, right?
Okay, I thought so now you have 4 descriptions.
I only have 2 descriptions.
But if you're dropping, you only have 1/4 of the samples.
I can produce 4 descriptions, right? But if I get only one,
Yeah. But I know you have only
Yeah.
one here, but
yeah,
you're producing 4 descriptions.
Yeah.
In the previous results, you had
2
2
descriptions.
descriptions.
Yeah.
Now you have 4. You're also changing.
Yeah. Okay. So here, then let's go
Yeah.
back to the.
He at most used just.
I can have 4.
One was you're using it, in the previous results you were doing checkerboard. Okay, here
Yeah.
you're having 4 descriptions.
Yeah.
Yeah. So here I can split that into 4.
Right.
But in all the results I presented, I only reconstruct 2.
At most.
The black and the shaded. Right. So I only reconstruct
Description 1 and 2.
2. Right. 1 and 2. Yes. 1 and
So you
2.
put 1 the central, 2 the side.
Okay, so when the one, let's see, the plots, the first
2
plots
is
you
the
showed,
central.
the ones
One
were you
is the
comparing
side.
references 1 and reference 2,
Mm-hmm. They have 2 descriptions.
meaning the description 1 and
Description
description
2
2.
only. Yeah. Okay. And references 1, reference 2 are different techniques, right?
I understand.
So we only compare at the total at the same rate. Right. So we only implemented our central decoder for 2 descriptions.
Okay.
Okay.
Okay, so I was pretty confused. What I thought a central
Decoder.
decoder would take all the descriptions.
Right.
Okay,
But I mean, here we just say this scheme can split 4, but
okay, I misunderstood. I thought you were doing a checkerboard. You said you did a checkerboard.
yeah, this is a checkerboard, right? This is a shade and this is black. It's a checkerboard.
Is 1 plus 2. Remove.
Yeah, but
Oh, okay. I see. That's where the confusion.
okay.
Right. So in other words, the 2 descriptions form a quincunx, right? Or form a half of a checkerboard, right? That's what. Right. But each description is
We only
1/4.
have something like 7 minutes, so I don't know how much material do we.
Oh, well, I'm almost done. Right. So in other words, now you see each side is only 1/4 of the original size, right? Yeah. So this is just 1/4. So if JPEG 2000 spent 0.3 per pair, for this side we spent 1.2 per pair, right? I mean that's a very good quality. And then of course, when we blow it up, we have a very good side information to work with. So
high rates you lose because you've lost the higher frequencies, right?
yeah, I mean all the loss is due to we cut off, right, by half. Right? I mean that is quite significant. So yes, indeed, you can see when the rate gets higher, we actually lose, right? Because then the radar the bit budget is not well spent, right? Because those bits should go to the high frequency coefficients. Our scheme does not allow that. So that's an inherent drawback. But for the low rate, you can see we gain, right? And for various images, you can see. Okay. Okay, so here you can see the visual comparison. This is JP2000. This is bicubic. Right. This is our side at the same rate, 0.2. This is very low, right? For this thing, of course, even for 0.2, JP2000 does an acceptable job for things like Nina, right? Other than some, ringing artifacts along the diagonal edges. That is understandable because it's, rectilinear transform. It's not adaptive. This is our reconstruction. This is bicubic.
It seems like JP2000 is doing bad rate allocation. I mean, if it allocated more to the lower frequencies.
No, I think it's due to the transform. So, for instance, people now have done the curvelet, right? Wavelet, directional lifting. Then those drawbacks can be somehow corrected. So, I mean, here the improvement in visual quality is even more prominent, right? And here, of course, we deliberately choose those structures that JP2000 or bicubic will do a lousy job, right? So here you see severe artifacts at this 0.2. This is low rate. Now the rate gets higher.
When you say 0.35, is just the subsampled image or the total image?
The total image. Yeah. For this bit rate, the JP2000 only gets this.
Actually, this is bike image, right? I mean, the basically the bamboo leaf.
Yeah, in part of that.
I recall that. I mean, in your basically result table is basically tables. 0.3 is at something like 24 for the bike, right?
This is for the I think this is for the leaf. Probably we cut off or cut off.
Okay.
So it's 32 dB kind of thing, right? So this is I wouldn't say that bit rate is too low, right? It's medium. I mean, even at the medium bit rate, some of the techniques, for instance, JP2000 doesn't do a good job, and we can have a significant improvement. So this is our side versus their. This is a single discretion now, right? Just as a conventional codec. And this is also. Okay, so this is and by the way, we know this is an interpolation thing, right? And we can do this enhancement after restoration, right? So to improve visual quality, this is an edge-enhanced version of those pictures for two different methods. Because, you can see for JP2000, because of the presence of those artifacts, if you do edge enhancement, the things get ugly. But with our technique, it's somewhat smoother, right? So then the result, after edge enhancement, you can have a sharp image without getting such, bad ringing artifacts. So this is a comparison. We also compare this technique against the DCT-based old JPEG. And at those bit rates, you see even black artifacts. Right, so this is JP2000, old JPEG, DCT old JPEG, this is the current technique. Okay, so I'm done. Here are the...
Thank you very much for the interesting presentation.
Thank you for your time.
Thank you very much.